Going on now to topic 6.3, logarithmic functions and their graph. We'll go to our first slide, take a look at the topics to be discussed, take a moment to read them, and we'll go on. Now, one of the background items in looking at logarithms is to see how they relate to exponential functions. And one of the things I'd like you to include in your notes is what they're showing us here, which I'll write it big here. 2 to the x power equals 8. This is the exponential form. And then later, we're going to go to the logarithmic form and take some background notes on this. And I'm going to modify this for a moment. I'd like you to see it in the whiteboard, that you're pretty familiar with 2 to the third power is 8. And if we describe this exponential form, it's a base, that is 2. The exponent is the 3. And the answer is 8. So here is sort of like a flow chart. Base to the exponent equals the answer. Now, when we put this in its logarithmic form, we're going to use the word log, which is an exponent. Logs are exponents. Here our base is 2. Our answer is 8, and that equals an exponent, which in this case is 3. So have this prominently displayed somewhere in your notes as background of what we're going to be doing, and we can go back now. We'll eliminate that for now, go back to our regular screen and follow the protocol that's given here. So we say we can solve this by using that technique of 2 to the x power equals getting the 8 into some base of 2, which is 2 to the third. If our bases equal each other, then the exponents equal each other. So here x is 3. Now, when you get to this one, we have 2 to the x power equals 9. Now, there's no way that we're going to be able to get a base 2 out of a 9. So we can't use this rather easy technique to do it. So what the mathematicians in the past have developed is a system of logs, where we use logs to find this. And of course, that's what we're going to be doing here in this lesson. Here are other formulas that we've used where we're involving exponents. Take a moment to read this, and then we'll go on. And the rest of it. Now, the items that we're going to introduce, where we had the traditional formula here, y equals a to the x. This is exponential. Our variable is x. If we switch these two around and we go x equals a of y, we're going to get what is called the inverse of this. And this value here is where we get our logarithmic function from. And the symbolism is described here, but read it carefully. The symbolism for the inverse is f with a -1. Now this is not an exponent. This is, and they're not multiplying, it's just the symbol to describe the inverse function of this. The inverse function of this is this, where we switch the x and y to around here. And you see that written. And that gives us then this inverse log of base a, and then the answer is x. So these that we described above are the formal way to show that we gave specifics for above, as this illustrates. So take a moment, get some notes. Now in example 1, they have it worked out for us, but we'll do it. And I'm going to go to the whiteboard. And we want to quickly review what we said earlier, that in exponential form, it's the base to the exponent equals the answer. In logarithmic form, it's the base of the answer is equal to the exponent. So in A, B, and C, they want us to put it from exponential to logarithmic. Take a moment, you do it, see what you get. So here our base is 2, so it would be log base 2. Our answer is 8, and this equals the exponent, which is 3. And again, we have to put log for all of these. We can just do that part, log. Now, what's the base here? Well, the base is 5. What's the answer? 625. And what's the exponent? 4. Again, here, this is a kind of symbolize our base is going to be 7. Our answer is z, and our exponent is x. Again, we're just following this protocol. This is going to be very useful later in the lesson and then in the practice and certify, and of course on your tests. Now, these are in its log form. We want to convert it back to its exponential form. So what is our base here? 3. What is our exponent? 2. What is our answer? And that would be 9. In example E, what is our base? 8. Our exponent is 3, and that equals our answer, 512. And then here's another symbolic one. What's our base here? 2. Our exponent, y. And our answer is x. And I've brought back the answers so you could see them here as the solutions. Now, notice when we say inverse, once again, we are switching these two around. So here we have in the exponential form, our exponent is there, and our answer is there. In the logarithmic form, our answer is there, and our exponent is there. Just some reinforcement here. As we go on to some more background, take a moment to pause and read this, and then we'll want to sketch these graphs, because as you do your certify, they will be asking you to select which graph matches that function. So you want to have some good background in graphic. Now, if you have your calculators or using Desmos to put this in, you'll get a picture of what the graph is like, but they'll be asking you to actually, do it. Now, you may recall this from an earlier section if we were to graph this exponential growth where our value is between, well, it's greater than 0, but less than 1, where it's a fraction, it has this general shape where it descends and then gets closer to our x-axis, which is our horizontal asymptote. That's the general shape of this. Now, what would the graph of the inverse of this, which would be its logarithmic form, look like? Well, they have that in blue. And that would be the function. Now, when you substitute values, you got this. And do you note anything? Well, here, again, any value to the 0 power goes through 1 on the y-axis for this, but on the x-axis for this. See it going through 1. And here we now have what is called a vertical asymptote, which is your y-axis. Again, the formula of the y-axis is x equals 0, and the horizontal axis here is, horizontal asymptote is y equals 0. That would be the x-axis. Okay. Again, some review. Now, on the next slide, we're going to take a look to see what the whole values greater than 1 would look like and their logarithmic form. Again, a little review, but get some good graphs down for this. And before we leave, we should mention too this dotted line here. The formula of it is y equals x. That is the axis of symmetry. Again, label as much as you want. Review is good. So this value up here referred to the graph that we had above. But now this one is y equals 2 to the x power. It's greater than 1. And you get this particular curve. And getting in its logarithmic form, and I'll just raise that up a little bit so we can see it together. There we go. There's the log form of it down below here. And notice there is still the axis of symmetry. Our horizontal axis is the axis, well, the horizontal asymptote. Our vertical axis is the vertical asymptote. There's our axis of symmetry. And you want to, again, be familiar with the graphing of these inverse functions. And I will raise it up just a little bit more so you can see the bottom here, hopefully. A little bit more anyway. All right. So you're pausing, getting some good notes. And then we want you to pause and read this caution here. I'll clear it up for you. Now, remember the domain and range of these. Let's just review that. The domain and range of the exponential function, remember this was from negative infinity to positive infinity, and the range, which was y values, never reached the 0, so we have a 0 comma positive infinity. But for the logarithmic form, the inverse of this, the domain is going to be, again, it never reaches 0. So it'll be parentheses 0 and then off to positive infinity. while the range now goes down to negative infinity up to positive infinity. Okay, background. Now for example 2, keep in mind there are videos by the author, and we'll take a look at that very shortly, but they're asking us to graph these two. Now notice this is a whole number. So what would the graph of this logarithmic function be like? Look at your graphs. Here's the graph of a fraction. We already know what those are going to be like. So as I scroll down to look at the answers, you'll see that the authors do this in their video. So this is the whole number graph, and this is the fractional number graph. And there is an axis of symmetry that goes right up there, and one is the reflection, in a sense, of the other. And notice they both go through 1, 0, but the shape of the graphs, again, if you fold it over the axis of symmetry, one would be on top of the other. Now let's take a look at the video and watch and listen carefully, and you may want to take some notes.
In the following examples, we will graph logarithmic functions. Our example says, sketch the graphs of the following logarithmic functions. A, f of x equals log base 3 of x. Note, once again, plotting a few key points will provide a good idea of the shape of the function. Let's create a t-chart of x's and y's. And we'll let x equal 3, 1, and 1/3. When I substitute these into the logarithm, I think those choices will be obvious. So when x equals 3, y will equal log base 3 of 3, and that simplifies to 1. When I substitute in 1, I have y is equal to the logarithm base 3 of 1. That will give me 0. And then for the 1/3, if x is equal to 1/3, y is equal to log base 3 of 1/3, which gives me -1. So I have the ordered pair 3, 1, the ordered pair 1, 0, and the ordered pair 1/3, -1. And I also know, because it's a logarithm, I have a vertical asymptote of x equals 0. And that would be the y-axis. So you can't actually see the y-axis if I dot it all in, but I'll just add some extensions that are dotted indicating the asymptote. And now I have 3, 1, I have 1, 0, and I have 1/3, -1. My logarithm graph, kind of missed that point, but looks about like so. It will head down to -infinity as x approaches 0, and it will head up to positive infinity as x approaches infinity. Example B, g of x is equal to log base 1/2 of x. Note, once again, plotting a few key points will provide a good idea of the shape of the function. Let's create a table of x's and y's. I'm going to let x equal 1/2 and 1 and 2. And then we'll substitute. Y equals log base 1/2 of 1/2. Gives me a y value of 1. So we have the ordered pair 1/2, 1. And then substituting when x equals 1, y is equal to log base 1/2 of 1. This gives me 0. So I have the ordered pair 1, 0. And then when x equals 2, we have y equals logarithm base 1/2 of 2, which gives me -1. So I have the ordered pair 2, -1. Because this is the graph of a logarithm, I have a vertical asymptote of x equals 0. In other words, the y-axis. The y-axis is already nice and solid, so I'm just going to provide a few extensions here to indicate my vertical asymptote. And we have 1/2, 1. We have 1, 0. And we have 2, -1. The base of 1/2 gives us essentially a reflected logarithm that looks about like so. As x approaches 0, my graph is going to approach infinity. And as x approaches positive infinity, the graph of this function is going to approach negative infinity.
All right, she did a nice job on that, and hopefully it's understandable. Again, you can always go back and watch it again. But again, if it's fractional, it'll have this general shape. If it's a whole number greater than 1, it's the reflection of this going the other way with our axis of symmetry still being y equals x. Going on now to example 3, we're looking at these 3 parts of example 3, and we want to do some transformations that we looked at earlier. Remember, we have vertical transformation and horizontal transformation. And just looking at these, we can pick up some things from them. I'm going to get a smaller stylus here. That this value out here indicates vertical transformations, and whatever number is here, it's going to move it vertically up 1. Here it's going to move it vertically down 2. And our basic shape of the graph depends upon what our base is. If it's greater than 1, it'll have this shape. If it's a fraction between 0 and 1, it's going to have this shape. Again, not very good. You'll get to see it. And there is a protocol to follow. And again, all you have to do when you do these is to pick them out from what they're going to show you. And keep in mind one other thing I think is of significance, is that if it's within a parenthesis next to the variable, here this says a +2, it's going to move it to the left a -2. And the same thing here, where it says a -1, it's going to move it a +1. Remember from earlier lessons when we did the parabolas, shifting and transforming those, when it's within, it moves it the opposite direction. If it's sort of in the y-intercept position, it moves it up or down. So let's take a look at the protocol for doing these. So take a moment. Again, I would sketch this in your notes. And they say the first thing is just to do this part, log base 3 of x. So that would be this red curve right here. And we just saw the young lady do this and got this general shape. It's a whole number, so it has this general shape with the y-axis being the axis, the vertical axis of the asymptote, I should say. Okay. Now, what do we see inside here? Well, we have a 2, that will be a -2. So we're going to take this spot, move it 2 in the opposite direction of +2, -2, which would be here, and then up 1, which would go here, and then there's that point. Now, this point, move it over 2 to the left, up 1. Okay. Over 2 to the left, up 1. And that's all you need to do in this transformation, know which directions and what's going on here. Now, we have a new vertical asymptote, which is now going to be x is equal to -2. So when we do our domain and range, domain is going to be, again, -infinity to +infinity. And the range will now be, it never reaches -2, but goes to +infinity. All right, that's the first one. We'll do the others in the same way. And part B now, there's our function. Again, it would be log of base 2, which would be the red shape. But now, because our x value in the parenthesis is a negative x, instead of going to the right, this one goes to the left with a new vertical asymptote of -1, because in a sense there's a 1 there, and it's away from the overall axis by going over 1 this way. So this one's a little tricky, so I'm going to clear it up, read it over. If you get one like this, again, you have a pattern to follow. In part C of this example, this one's a little more straightforward. Now again, we want the graph of this. What does that look like when it's a fraction? Well, it's the one in red. Okay. Now notice this is not in parentheses. So it's not going to be a horizontal shift, but it's going to be a vertical movement where our y-intercept has gone from what it would have been 0 here down 2. So there's our 0. It's just going down 2. Where it was, it's going down 2. Where it was, it's just going down 2. Okay. And again, the range and domain of these actually are the same. As our first example, which was parenthesis 0, doesn't reach 0, that's your asymptote, to +infinity, and then range from -infinity to +infinity, that is all real numbers. Okay, let's go on. Here is some background information. Pause, look it over. Let's go on. And now we're going to evaluate these following logarithmic expressions. And again, what would be the protocol for it? Well, we'll start off easy. Let's put this in its exponential form, which would be our base is 5. We know the answer is going to be 25, but we don't know what, in a sense, we could say this equals x would be. So again, for this one, we can use that old-fashioned method, or the older method. 5 to the x power equals 5 to the second. X is going to equal 2 here. All right, in example B, converting it to its exponential form. So our base is 1/2. Our answer is 2. What would our exponent be? Think about it. This one also has a base of 2. and that would be -1, because 1/2 to the -1 power is 2. Now, and I'll switch to the book because they have it worked out nicely here and saves me a little bit of writing. So there was the original. Now, how can we put this 8 as to some base of 4? Well, 4 to the 3/2. And remember, if we convert that to its radical form, this denominator becomes our index number 2 that we don't write. This is our radicand, and then this is raised to the 3rd power. So the square root of 4 is 2. 2 to the 3rd is 8. That's where they get this from. So here our x value would be 3/2. That one was a little challenging. Now in letter D, we have the log base pi, and then the answer, the square root of pi. So here we're going to convert the square root of pi to a fractional exponent. So there's our base then. Our index number is 2 that we don't write, but it's to the 1st power, so this becomes pi to the 1/2. So our x value here would be 1/2, and that's how it would look. So these are equivalent. In letter E, we have 17 is our base. The exponent is 0, and it's 1. So in exponential form, it's going to be 17 to the 0 power equals 1. And here, looking at this, we have log base 16 of 4 is equal to the log 16. And again, 16 to the 1/2 power is equal to the square root of 16, which is equal to 4. So our exponent then, our x value, would be 1/2. And then in letter G, and I'll pause and bring this up a little. And some of these get a little challenging, so look it over. Now, the base 1/9, 1/9 to the -1/2, again, keeping our rule of exponents, this would be, to make this exponent positive, we have to take the reciprocal of this, which is 9 to the 1/2 power. So 1/9 to the -1/2 becomes 9 to the +1/2, the reciprocal, which is 3. And our exponent then would be -1/2. And here, 1/100th, the same pattern. This is going to be 10 to the -2. And our exponent is -2. So these are a tad challenging. They have the protocol here, and hopefully what I've done is helpful. Okay, going on to solving elementary logarithmic equations. We're going to have 3, and I'll do these on the whiteboard for you. Okay, going over part A here. There's our basic function. We want to convert it to its exponential form. So our base is 6. Our exponent is a -1. And that equals the answer 2x. Now, as we solve this, we know our 6 to the -1 is going to be 1/6. So I can use my eraser and convert that to 1/6. And now to solve it, I'm going to divide both sides by 2, or I can do a little fancy math. I'm going to multiply both sides by 6 to get rid of that fraction. So I get 1 equals 12x. So x will equal 1/12. Now I'm going to the whiteboard. This is a little bit tricky. And in the instructions, they tell us to convert this to its log form. So it will be this part here. Converting this side to its log form, we get this. So now we have log of base 3 to the x base, log base 3. Our answers equal, so our log values should equal each other. So that would be 3x equals 3. Dividing by 3, we get x equals 1. And let's go back and check it out. And I'll get rid of this. And we see there it is, x equals 1. All right, now for our last one, I'll do that as well, but we can look at what's in the book. And in lesson or part C here, this was the original. We're going to convert this to its exponential form, where our base is 2, our exponent is 5, and that equals the answer, which is 8 to the x power. So we want to get this 8 into a form of base 2, which is going to be 2 to the third power, and then the x is still out there. Use the powers property, we're multiplying. The 3 times x gives us this. So now our bases are the same. So our exponents should equal each other. This would be 5 equals 3x. Divide both sides by 3. We get x equals 5/3. And if we look at what's there, we get x equals 5/3. And this was the protocol. All right, just 2 more slides to go and we're complete. This is rather a long lesson. Some more background material. Pause, read it over, keeping in mind that you need to be able to use your calculators properly. And there are 2 basic keys on your calculator. The first one, referred to as the common log, and that is base 10. And generally it's not written if it's in this log form. The other is the natural logarithm, which is the natural log is base e, and it's written ln, and that would be base e. Again, we don't write that e if it's natural log. You might say, how come it's not nl? Well, because in Latin it's logrimus naturalis. So pause, continue to read this over as needed. I'll raise it up a little. And again, these are all in your learn sections as well, showing you how to put the log form into your calculators and it graphs them. We'll also do this on Desmos. Now notice these properties of natural logs also applies to common logs, but write these in your notes. Pause, take a moment. I'll go over them with you. So the natural log of 1 is 0, because when we put that in its exponential form, anything to the 0 power is 1. Now, the natural log of e, base e, remember, we don't write that, of e is also, well, in this case, is 1. Not 0, but it's 1. So this configuration that we're going to use and see as we do other examples, this configuration is 1. Now they're only putting the 1e there, but there is an unwritten one there too. So that in its exponential form, this would be our base is e. E to the first power is our exponent, and that is e. So e to the first power is e. What's the exponent of it? 1. Every letter, every number has an unwritten power of 1 there. Now, when you have this arrangement, in which it's the natural log of e to the x power, that actually just equals your the exponent there. Because the rule is we take this e when we convert it, and we put that x out in front here as x. This, we know, is just 1. So x equals x. Now there's a little bit more math here, but just remember this configuration. This part is 1. The x would actually go out in front. X equals x. Now here, if you have the e, natural log of e, this also equals x when it's in this form. Now they didn't put the natural log out here, but they have natural log written as an exponent in a sense. And that equals x as well. So a couple of things to remember as we work these through in other equations. As we go on to our last example, number 6, there are 4 items here. And let's just go to the solution. Shorten this a little bit here. So for something like this, you don't need a calculator for this. Remember, in its exponential form, this is going to be e. There's a 1 there. And our index number is 3. So this just becomes e to the 1/3. Now in item B, we have log 10 to the 3rd. So our exponent is going to be 3 because 10 to the 3rd power is 1,000. Now for this, we're going to need a calculator. You have to put the natural log key in. A parenthesis comes up. You put in 4.78 close parenthesis, and then you round to 3 decimal places. Remember, this is approximation. And then that would be natural logs. And this one, using the log key, common logs, base 10, log comes up, parenthesis, 10.5, close parenthesis, round to 3 decimals. Okay, we'll be doing the practice next, and hopefully that'll give you a chance to work these yourself and absorb this. The nice thing about it, I think, is you can watch it again if needed.